Scintillation detectors are devices used in radiation detection and measurement. They employ a scintillator material that emits light when exposed to ionizing radiation. This emitted light is then detected and converted into an electrical signal. Scintillation detectors are widely used in various applications including medical imaging, nuclear physics, environmental monitoring, and radiation protection. Here is an overview of scintillation detectors, their types, working principles, and the principles behind detecting alpha, beta, and gamma radiation. Organic scintillators typically have a higher sensitivity to low energy radiation, but they have a slower response time compared to inorganic scintillators. Inorganic scintillators are made of crystalline materials such as sodium iodide, cesium iodide, bismuth germanate. They offer better energy resolution, higher light yield, and faster response time compared to organic scintillators. Working principle: when ionizing radiation such as alpha, beta, or gamma rays interacts with the scintillator material, it transfers energy to the atoms or molecules within the material. Excitation and de-excitation: the observed energy causes the atoms or molecules in the scintillator material to become excited. This energy is quickly transferred to electrons in the material, raising them to higher energy levels. Subsequently, the excited electrons returns to their ground state through a process called de-excitation. Light emission: during de-excitation, the excited electrons release energy in the form of photons, visible or ultraviolet light, in a process known as scintillation. This intensity of light emitted is proportional to the energy deposited by the incident radiation. Photo detection: the emitted light is then detected by a photosensitive device, typically a photomultiplier tube, which converts the photons into an electrical signal. PMT has photocathode. The photocathode is photosensitive material that absorbs photons and emits electrons through a photoelectric effect. Common materials used for photocathode include cesium antimonide or bialkali compounds. Electron multiplier: the emitted electrons from photocathode are accelerated and focused onto a series of diodes within the PMT. Electron multiplication: as the electrons strike the diodes, they cause the emission of additional electrons through a process called secondary emission. This multiplication process occurs sequentially across the diodes, resulting in a cascade of electrons, amplifying the initial signal. Anode: the amplified electron signal reaches the anode, which collects the electrons and generates an output current or voltage proportional to the incident light intensity. Alpha, beta, and gamma detection principles. Alpha detection: alpha particles are positively charged and have a high ionization power. To detect alpha particles, a thin window or membrane made of material with a low atomic number such as mica or mylar is used. The thin window allows alpha particles to pass through and enter the scintillators, where they deposit energy and generate scintillation light. Beta detection: beta particles are high energy electrons or positrons. To detect beta particles, a thicker window or a solid material such as plastic or metal is used to prevent their penetration. The beta particles interact with the scintillator directly, depositing energy and generating scintillation light. Gamma detection: gamma rays are highly penetrating electromagnetic radiation. To detect gamma rays, scintillation detectors employ material with high atomic numbers such as sodium iodide or cesium iodide. The type of radiation being detected determines the window design and the scintillator material used in the detector. Thank you for watching.